Hello everyone, I'm Norman Wahlberger. We're here at the University of New South Wales, and today I'm going to carry on with our brief introduction to projective geometry, especially oriented towards understanding conics and then quadrics later on. So the setup that we were aiming towards last time involved a very sort of simple-minded kind of algebraic understanding of projective geometry. So we had things called points or projective points, and they were things of the form x, y, z, where there's really a proportion, but this is to be thought of as a projective row vector. And by that we mean that it's invariant under scaling. And let me say in another way what that invariant under scaling really amounts to. So we say that say x1, y1, z1 equals x2, y2, z2, precisely when. So these two proportions are going to be equal if the proportion of this one to this one is equal, if the proportion of this to this are equal, and if the proportion of these two to these two are equal. So we can write that as x1 y2 minus x2 y1 equals 0, and y1 z2 minus y2 z1 equals 0, and z1 x2 minus z2 x1 equals 0, when all three of these conditions are satisfied. That's another way of rewriting the statement that one of them is a multiple of the other. All right, so those are projective points, and then we also had projective lines, and they were objects that were expressed in terms of column, projective column, and the same kind of equality is defined. And then we had the incidence relation that P lies on L, or equivalently L passes through P, or just more symmetrically, P is incident with L. That's the condition that as matrices, P times L equals 0, which amounts to the condition that Lx plus My plus Nz equals 0. Then we also had the idea of joining 2 points. So if P1 and P2 are both points, then we define their product, P1, P2, to be the line, well, exactly with these kinds of coordinates. So the first one will be y1, z2 minus y2, z1, and then z1, x2 minus z2, x1, and then x1, y2 minus x2, y1. So I should have said at the beginning that when we're talking about a projective point like this, we have to satisfy the condition that not all three of them are 0. So they're not all 0. In other words, we're not going to consider the projective point 0, 0, 0, because in our minds that doesn't correspond to a one-dimensional subspace of the three-dimensional space. Okay, so we have this condition for the product of 2 points, and we have a similar condition for the product of 2 lines. So if L1 and L2 are lines, then their product is the point, and I'll use the same notation that I have here with little l's, m's, and n's. So the product is going to be m1 n2 minus m2 n1, and then n1 L2 minus n2 L1, And then I suppose L1 M2 minus L2 M1. And it's these conditions here that, that guarantee that if these two are distinct lines, or these are distinct points, then this is actually well defined. So I probably should officially say these have to be disjoint or distinct lines. These have to be distinct points. Okay, so that's good. So it also allows us to say a little bit more than I said last time. We can now introduce the idea of collinearity. So then we can compute that, say, if P1, P2, and P3 are points, then P1 lies on P2, P3 precisely when the determinant P1 is x1, y1, z1, and then x2, y2, z2 is P2, and x3, y3, z3 is P3, precisely when that determinant is 0. And why is that? Well, because if we take, say, the dot product, if we ask when is P3 lying on this thing, P3 will lie on this when the dot product of P3 with this is 0. And that's exactly how we evaluate this determinant if we're expanding along the bottom row. And this makes it obvious that this is a symmetrical, so this is now a symmetrical condition, i.e. it's the same as P2 lies on P1, P3, or P3 lies on P1, P2. So collinearity of points is just a determinant condition. That's a consequence of the way we define the product. And dually, if we have three lines, so if L1, L2, L3 are lines, then say any one of them, L1, passes through L2, L3, precisely when a similar determinant is satisfied. And I might write it like this: L1, M1, N1, L2, M2, N2, L3, M3, N3, because these are, after all, columns originally. That determinant is equal to 0. All right, so this is a very simple and elegant way of thinking about two-dimensional geometry. It's a very simple and elegant way of computing with two-dimensional geometry, because the basic operations are all encoded in a cross product, and the basic notions of collinearity and concurrency are encoded by determinants. So let me remind you of the picture that we have in mind for all of this. We actually motivated all of this by original picture where we had our familiar x, y, z space. And we had the plane z equals 1 with local coordinates little x and little y. And a projective point was just a line through the origin. That's a projective point, something like x, y, and z. And where it actually meets our viewing plane is where we're actually going to visualize it. And a projective line is a plane through the origin. That's something like L equals L, M, and N. And that will be visualized in terms of a line. And if we want to be explicit, this point is going to be the point x over z and y over z in the ordinary two-dimensional plane. And this line is going to be the line with the equation Lx plus my plus n equals 0. Okay, so we're not always going to draw this three-dimensional story, though. Usually we just want to draw this two-dimensional plane. So let's draw it over here again. Little x and little y. But this is now the projective plane. So it means it also kind of includes points at infinity. And let's just orient ourselves a little bit by giving things names which are more in keeping with the notation that we're talking about here. Okay, so this point here, for example, this unit vector point, ordinarily we would write it as 1, 0. But in this projective setting, we would write that as the point 1, 0, 1, with no commas. This ordinarily would be the point 0, 1, but now we are going to write it as just 0, 1, 1. And in fact, if we have any point which has ordinary coordinates x, y, we are going to represent it with the projective triple x, y, and 1. Now if we have some line, let's say going through 2 and 3, so there's a line. If it has x intercept 3 and y intercept 2, then its equation is going to be, the usual equation would be 2x plus 3y equals 6. So let me write it as minus 6 equals 0. And now I'm going to just write that with our notation. So that's really the same as the projective column 2, 3, minus 6. Yes?
Do we not have the commas at 0, 1 for the projective notation?
Exactly. No commas. Thanks. Okay, so that illustrates points and lines, but there are also some other points and lines in this picture that we didn't have in the usual framework because there are points and lines at infinity. So let's talk about them. So if we go in this direction, say this is a convenient direction, and it has a direction vector, say minus 3, 2. So there's a vector minus 3, 2. If we go in that direction and we get to the point at infinity, here's infinity, then this point in this direction is going to have coordinates. It's a point, so it has row coordinates, minus 3, 2, and 0. How do we know that this line passes through that point? We just take the product of these two things. Minus 3 times 2, plus 2 times 3, plus 0 times minus 6, that's 0. Therefore, this line does pass through that point. Notice that any other line which is parallel to this one, for example, maybe 2x plus 3y plus 5 equals 0 or something like that. That's going to be parallel to this one. It will also pass through that same point at infinity. All parallel lines pass through the single point at infinity. So there's one point at infinity for every family of parallel lines. And it's probably not good to think of the point at infinity being necessarily in this direction. It's equally in this direction down here. These two directions are sort of symmetrical and represent the same point at infinity. So there are also points at infinity exactly of this kind where we have some x, y, and a 0 z coordinate, but there's also the line at infinity. Okay, maybe I should draw that red. Okay, that line at infinity, what will it be? Well, first of all, let's just talk about the x-axis. What's the x-axis? That's the line y equals 0. And so that will have coordinates 0, 1, 0. Because it represents the equation 0x plus 1y plus 0 equals 0. While the y-axis has equation x equals 0. And when we write down a column vector for that, we get 1, 0, 0. And what about the line at infinity? Well, it's those points whose z-coordinate is 0. So its equation, if you like, is z equals 0, because it corresponds over here to the xy plane. And if z equals 0, that corresponds to the column vector 0, 0, 1. So this line at infinity somehow plays a complementary role to the x and the y axes, which is not surprising if you go back to the original three-dimensional story. Okay, so this is projective geometry, the projective plane. No, so what we're doing is we're looking at this story here, and we're saying our projective plane is really this plane here, together with a few more points at infinity. Because our original understanding was that the projective plane was actually lines through the origin. And that's probably what you should think of it as really being. But that's hard to visualize, and so we prefer to think of it as being this plane together with a few extra horizontal lines. So the sort of discontinuity has to do with the choice of this particular plane as a viewing plane. We're really interested in this family of lines, and we could have chosen, in fact, any plane to visualize those lines. It was a rather arbitrary choice to choose this particular plane. Traditional but arbitrary. All right, so let me show you how this is very useful when we're talking about transformations of the plane. So it's actually vitally important in video game design and things like that, robotics, because this picture is a bigger picture than the usual picture that we have in linear algebra. Okay? It's a bigger picture because we're looking at essentially a two-dimensional story, but in a three-dimensional context. We have 3 dimensions really working for us. So if we have transformations, we should say. So if we have a typical transformation of the plane, x, y goes to, say, x prime, y prime, which is given by x, y times some matrix A, B, C, D. Maybe I'll write as a matrix vectors. There's a typical linear transformation in the plane where we're multiplying a row vector by a 2 by 2 matrix. That can be incorporated in the story or represented. So this linear transformation is represented by homogeneous coordinates by thinking of x, y, z going to x, y, z times the 3 by 3 matrix A, B, C, D with a 1 in the bottom. So if you think about how this linear transformation acts on three-dimensional space, what it does is it transforms x and y in the standard way and then leaves z fixed. And so it's just acting essentially on this two-dimensional plane in the standard way. So linear transformations can sort of obviously be incorporated, but the advantage is that translations can also be incorporated. So if we have the transformation that takes xy to, say, x plus a, y plus b, for a fixed a and b, this is a translation of the plane. And that's usually outside the strict domain of linear algebra, because linear algebra concerns itself with transformations that always leave the origin fixed. So if you want to work with this kind of transformation in conjunction with linear transformations, it can be a little bit awkward because you're mixing apples and oranges. But however, in this three-dimensional context, this is represented by sending x, y, z to x, y, z times 1, 1, 0, 0, 1. And put an A here and a B here, zeros here. So let me write out what this is. If we do the multiplication, this is x plus az, y plus bz, comma z. But if you restrict yourself to the z equals 1 plane, then this linear transformation acts as a translation in the z equals 1 plane. So that means that a video game designer can deal with translations of the plane and rotations all with the same technology, all with 3x3 matrices throughout. Okay, so that's pretty interesting. But today I really want to introduce a conic into the story. Okay, so the conic makes everything much more interesting. And we end up, surprisingly, going back to the ancient Greeks and their understanding of conics. So now we add a conic. To our projective plane. And I remind you that we're going to think about things homogeneously, and a conic for us is going to be represented by a 3x3 matrix, and I'm going to use this form: A, B, C, D's here, F's here, and G's here. Okay, it's actually going to be a homogeneous thing, so I should probably use square brackets. So if I put a x, y, z over here, and I put an x, y, z over here, then I get, set that equal to 0, then I get the standard homogeneous form for a conic that we talked about last time. Let's call this matrix A, so a projective matrix A, and this thing here might be P and P transpose, so we're talking about P times A, P transpose, equaling 0 as an equation for our conic. Yes?
How does that equation change their linear terms in x or y and z? Because I've seen conic equations with those.
Okay, so let me remind you how this connects to the standard story of a conic. If we expand this out, we get A capital X squared plus B capital Y squared plus C capital Z squared plus 2D times XY plus 2F times XZ plus 2G times YZ equals 0. And then if we divide by Z squared, We can write it in non-homogeneous form in terms of little x and little y as ax squared plus by squared plus 2dx plus 2f. 2dxy plus 2fx plus 2gy plus c equals 0. So the linear terms in the usual formulation are sort of encoded in these terms here with the z powers there. Okay, so this introduction of a single conic into this story really expands our thinking dramatically, okay, and opens up all kinds of new considerations. Because this conic can sort of be identified with this quadratic form. And quadratic forms are really the same as symmetric bilinear forms. And this is really all not very far away from what's usually called a metric, or let's say metrical structure. Okay, so let me put all of that in quotes just as something to orient us. Okay, so probably the best thing to do is to take this matrix A, start out with, and to recognize that the 3 by 3 matrix A determines a symmetric bilinear form, which is usually called a dot product, or sometimes called an inner product, but best called a symmetric bilinear form. They all mean roughly the same thing. On three-dimensional x, y, z space. And that is just by defining the dot product between two vectors to be v times a times w transpose, where all our vectors are, as usual, row vectors. So the usual dot product is just the case, the special case. The usual one is the special case when the matrix A happens to be the identity matrix. But there are lots of other interesting ones. And another one that's very important for differential geometry is a relativistic one. So another example, if A is equal to 1, 0, 0, 1, minus 1, then the dot product looks like x1, y1, z1, dot x2, y2, z2 equals x1, x2 plus y1, y2 minus z1, z2. So that's a dot product or bilinear form that's essentially relativistic. Or it also goes by various other names, sometimes Lorentz or Minkowski or Einstein. And this kind of inner product plays a crucial role in special relativity, admittedly in one dimension up, in 4 dimensions rather than 3, but the story is somewhat similar. And for us in this course in differential geometry, we have our eye on physics, and so relativistic applications are important for us. And so this is a very interesting kind of inner product for us. All right, but this is an inner product on the 3-dimensional space. How do we convert that into something on our projective plane. So here's our usual picture again. Our z equals 1 plane. Okay. So we have this now, this dot product. So that means that given any two vectors, say v and w, in our space, we can form v dot w if we're given some fixed matrix A. So we assume A is fixed. It's a fixed 3 by 3 symmetric matrix. So v dot w is v a w transpose. All right, so that's a structure in the three-dimensional space, but we want to think about what it looks like in the two-dimensional projective plane. Well, when we're doing that, we're looking at lines. So we can look at the lines through v and w, and they will intersect in 2 points here. So does it make sense to talk about the dot product between these 2 points? Well, not really, because these 2 points are just representing these entire lines. We're not actually talking about this particular vector and this particular vector. These 2 points that we're drawing represent the entire lines. So it doesn't make any sense to say it's this vector dotted with this vector. So we don't get an inner product on our two-dimensional viewing plane. But we get something more fundamental and basic. The thing that's projectively invariant here is perpendicularity. So I remind you that when we have an inner product like this, we can define perpendicularity in terms of the dot product or inner product. So perpendicularity is defined by v is perpendicular to w precisely when v dot w equals 0. And that notion makes sense projectively. This makes sense projectively. So in other words, what we're going to do is, so definition, if a 3 by 3 symmetric matrix is given, we define P, say for P1 and P2 projective points. We'll say that P1 is perpendicular to P2 precisely when? Well, when P1 times A times P2 transpose equals 0. So even if you multiply P1 by a scalar, this condition is not going to change. Being 0, that condition doesn't change if you multiply by a non-zero scalar. That's a projective or homogeneous condition. So this is usually called polarity. And let's see what it looks like geometrically. So if we have P1A, P2 transpose equals 0, we can write that as P1 times A P2 transpose equals 0, or P1 times, say, L2 equals 0, where L2 is A times P2 transpose. In other words, the condition is just the condition that the point P1 lies on the line L2, where L2 is determined from P2 by this transpose multiplication by A. Let's have a look at an example. So let's do the simplest case, perhaps, when the A is the matrix 1, 1, minus 1. That's actually the relativistic story. And the associated conic is x squared plus y squared minus z squared equals 0. Or in ordinary x, little x and little y coordinates, x squared plus y squared equals 1. It's just the unit circle in the plane. So there's the unit circle. So what does this perpendicularity look like? Let's choose a point. Let's choose the point, say, 2, 1 right here. There's the point, ordinary point 2, 1, which is the same as projectively as 2, 1, 1. And let's look at, let's call this, say, P2. It's going to play the role of P2. So let's look at what we're calling L2. What is L2? It's the matrix A times P2 transpose. So it's 1, 0, 0, 0, 1, 0, 0, 0, minus 1 times 2, 1, 1. And that is 2, 1, minus 1. So what is that? So P2, this A, this L2, let's draw it. It really is the line 2x plus y minus 1 equals 0. 2x plus y minus 1 equals 0. What does it pass through? If x is equal to 0, y is equal to 1. And if y equals 0, x is equal to a half. And I'm going to call this L2. I'll give it a name. I'm going to call L2. I'm going to define it to be P2 perp. All right, so what's the relationship between this point and this line? Well, according to this inner product, all of these points that are on here, any point that lies on this line, will be perpendicular to this point under the inner product given by this matrix. Right? So we choose any point on this line. Let's say this one here. This happens to be 0, 1, 1. And if I take 0, 1, 1, and I take multiplied by this matrix, and then I multiply it by 2, 1, 1, I should get 0. Let's just check if that actually works. So 0, 1, 1 times the matrix times 2, 1, 1. What is that? Well, when I multiply this, I just get 0, 1, minus 1, and then I'm multiplying by 2, 1, 1, and I get 0. So what we have here is that if we start with a matrix A, we have a new notion of perpendicularity that's a projective notion of perpendicularity, which actually goes back to Apollonius. Okay? This notion goes back to Apollonius. Who realized that if you have a conic, probably the most important property of a conic is the following. Here's an arbitrary conic. And if you have a conic, let's call it C, then to any point P, you could associate a line. What was the line? The line is the line that you get by drawing tangents. seeing where the tangents meet, and drawing that line there. So Apollonius probably would not have objected if we call that P perp. So for every point P, there's a corresponding line. This is a key feature about conics. It's a fundamental fact of life about conics that unfortunately people don't get taught in schools, although they used to. Yeah?
Which line would Apollonius attribute to a point that was lying within the conic itself?
That's a very good question. Okay, so the question is, what would be the dual of the point inside? What would be the polar of such a point? Well, to answer that, let me go back to this formulation here, and to observe that because the matrix A is symmetric, this is a symmetric relation. Okay, so that if P1 is perpendicular to P2, then P2 is also perpendicular to P1. So, for example, if I drew the perpendicular of this point, let's call this one P1 for the sake of argument. The perp of this one has to pass through this point because the perp of this one passes through this one. So if I want to look at the perp of P1, I would get a line that looks something like this. This would be P1 perp. If I took another point down here, let's say call it P3, then if I took its perp, I would get that line. So the answer to the question of how could you find the perp of a point inside is to draw two lines that pass through it and draw their poles, is the term used. Draw the tangents here, that would be one of them, and then draw the tangents here, that would be another one, and then to join those 2 points there, that would be then Q perp. Okay, so a key point here is that the symmetry means that if P1 is perpendicular to P2, well then P2 is perpendicular to P1. And so that implies that if P1 lies on let's write it this way. P1 lies on P2 perp precisely when P2 lies on P1 perp. All right, let me try to explain this from a three-dimensional picture, which I think is instructive. So let's go back to the original x, y, z. And I'm actually going to use this same relativistic form because it's good for us to think a little bit relativistic. So here is the cone. X squared plus y squared minus z squared equals 0. That's a cone in three-dimensional space. And it meets the plane z equals 1 in z equals 1 in the unit circle. So that's just the unit circle, little x squared plus little y squared equals 1. Now in special relativity, this cone is called the light cone. And it corresponds sort of to the motion of photons. This is roughly an axis that's time, and these two directions are roughly the spatial directions. And, okay, this cone is intimately connected with Einstein's theory of special relativity. And the matrix And the dot product that's underlying here, so the dot product that we talked about before, x1, y1, z1, dot x2, y2, z2 equals x1, x2 plus y1, y2 minus z1, z2. What does that dot product look like? Let's say you have a vector. What's the perpendicular plane for it? So if I choose a vector like this, and ask what are the vectors that are perpendicular in this sense to that vector, I'm going to get a plane. But the plane is not going to be perpendicular in the usual sense. It will in fact be sort of symmetrical. So this is actually what that normal plane looks like. And if I intersect these two things with the viewing plane, we intersect this line with we would get a point like that. And if I intersect this plane, we would get a line. And these would be exactly the polarity of Apollonius with respect to the unit circle. So what happens is that if we go back to the unit circle picture here, if we have a point P like this, then its polar line is like this. If P gets closer, let's say to a point Q like that, then the polar line gets a little bit closer to it. And in the limiting case, when we have a point that's actually on the conic, then the polar line is the tangent. So, theorem, if R is on the conic, the polar line is equal to the tangent. I'll talk about that theorem next time, and we'll see how this relates to, well, we're interested in parabolas in particular, because we want to talk next time about curvature of parabolas, and we're going to see that this inner product that's underlying the conics helps us a lot in doing geometry with parabolas. So see you there.